Gentlemen, welcome back to the shop. Today we're going to have a look at the inwards of this Milwaukee. Now, as a fully grown ass man, I wouldn't even have managed in years past a sneer out of my overly jaded countenance at this Milwaukee play toy. You know, it's a Dremel, and we all know that the Dremel is the smaller brother to the actual tool, which is a die grinder. The only problem is this thing, it's like jamming a 454 4-barrel in a Suzuki Samurai. You turn her on and she goes like a raped ape, which is great for welding and heavy fabrication projects because you're not dicking around. But this small little tool actually, once I bit the bullet and bought it, actually comes in handy, especially for aluminum casting, making the molds or the patterns out of foam, as well as quickly and delicately removing material from plastics of all sorts. So for small rocket surgery grade projects, this actually does come in handy. And of course the team colors match my eyes, so there's that. Now before we get into the meat of her, it does have speed control. I'm going to turn it on. And you hear that high-pitched whine? That tells me that this is MOSFET controlled. So there'll be a microcontroller in here turning a MOSFET on and off at a pulse width modulated signal. All that happens when we speed it up is that the duty cycle of that waveform gets longer. So the average voltage goes up. Actually, instead of doing all that nonsense, let's just use our telephones. Good enough for the girls I go out with. I mean, they're amazing devices. Now here's an app I just downloaded. There's many different flavors of this app, but this one shows the peak. So we should see, yeah, there's the carrier frequency right there, and you can hear it at 3,900 hertz. So that's that high-pitched whine you can hear when you start up tools that have that kind of control, that have electronic control, that aren't just ka-chunk, ka-chunk on off. And that's the carrier frequency, well within audible human hearing range. Irritating as hell. And the carrier frequency isn't changing, it's just this is measuring the peak, whatever's the loudest, and the fan noise is going to be the loudest, and that's what we're hearing there, and that's what's moving around. Yeah, this app isn't that good, but as with all modern tools, they all use torque bits, so it's good to have a nice set of Torx bits. You can buy the inserts, of course, the little bits. Unfortunately, for some tools, the little bits don't fit in the hole. They're not long enough. You know, sometimes you need a long reach. So it is worth investing in a good set of Torx. Oh, this is a new feature. Here's a steel clip, and you actually can't get this apart because it's dovetailed in there. You got to bend this clip up, and then it'll slide out. Little trap for young gamers. Of course, when we put her back together, we'll just rebend that tab. Okay, we got her all disrobed, and surprisingly, for such a light-duty tool, it's reasonably robust. It's surprisingly robust, actually. We can see here the plastic is nice and rigid. It's, of course, it's the PA6, which is nylon glass fiber reinforced, 30% glass fiber reinforced, makes it rigid and nicely impact resistant. And also, it's got the thermoplastic elastomer, over molding. And here's an interesting feature, what for keeping it from peeling off. They've actually got holes in the PA6, which is the nylon, in order to make sure that it sticks on there good. Which is interesting because this is a styrene based, not a urethane based, so it's got styrene, the same kind of, you know, the cheap plastic cutlery. It's got that molecule in there, and they add a few atoms on the end, and it makes it an elastometer, like a rubber. I can't say that word for the life of me. Now, of course, you look at this, it makes sense that it needs to be rigid on account of the casement's the only thing holding in this big beefy motor here and the small little bearings. The thing turns at 37, rated 37,000 ripums. She'd make one hell of a hoo-ha rattle. You'd never be able to find the thing. It'd be in your wife's nightstand. Now, speaking of hoo-ha rattling, if you turn this, you can see that it's cogging. So it's got to be a permanent magnet motor. And it's not brushless because, of course, it's not slathered with brushless labels on there. So it's got to be a brushed DC motor, but a permanent magnet. You can see the shaft looks nice. It's all been ground. However, one feature that I don't like is this is the locking pin here that's got to go in. And it goes through this sintered powdered metal bushing. So that's kind of nice. And that's a big skookum bushing. So when you're reefing on this to lock it in, this is what's taking up all the torque. However, you know, you don't want to bend this shaft, but you could easily do that. If we see, the devil, of course, is in the details, and if we see here the shaft, the one side chamfer is nice, and then the other side chamfer is pretty hideous. So something with the process, this must be a manual process just for deburring this, and somebody didn't do a very good job on that. And I did the old jazz hands routine on the gargler with this number. Couldn't find anything, but it is a, as you can see, permanent magnet brush DC motor, 4 poles, 4 magnets, and actually the windings on the rotor are quite robust. And this is a reversible motor as well. We don't use it reversibly, but it will go both directions. And you can see it's built that way because the fan blades are bidirectional. So if you were to destroy all the electronics on this, you could get away with using this for something else. And they've added some nice details that you don't normally see. They got a little condom on the back here, on the back of the bearing to keep the dust out. Now these are just spade connectors, of course, but they've added some mechanical strength by putting on the heat shrink, and there'd be hot snot glue in there as well. So the heat shrink it on, and that helps to keep the connection good. And then they've also added, this is a nice feature, this fiberglass matting, well, this fiberglass protective, high temperature protective tubing. So that's very nice. Getting onto the circuit board, we have some interesting features here, stuff we haven't seen on this type of tool before. Here's a big Schottky diode. This is like 12 amps rated. And of course the Schottky diode, rather than a regular rectifier diode, is much quicker at recovering. So it's a faster diode. So what would they be using this for? Because we don't need any, it's on a battery, so it's already DC. We don't need any kind of rectification or anything like that. So that's interesting to keep in mind, that Schottky diode. We'll get back to that. Here's the brains of the operation, Atmel Mega. I mean, I would say overkill, but this is probably what they use in all their tools, so it's easier for their design team and their manufacturing. Also likely get volume, you know, they hit their volumes if they use the same type of chip on microcontroller on every single board. Here's an International Rectifier 1404Z. This is a MOSFET. This is in the D squared package. We have the same thing here on the back side. But this one, if you look at this one, it's got a whole bunch of heat sinking, and it's electrically isolated from the heat sink. So the source is electrically isolated from the heatsink through this special compound here that allows heat to go through, but not electricity. And you can see this huge monster brass heatsink here. I mean, there's no lack of heat sinking, and you'll also get some cooling effect from the fan, it being so close to the fan here. Of course, it sucks air in through and blows it out. And then here's the switch that actually tells it to turn off and on. Now this doesn't switch all the power, so you can see it's a tiny little anemic micro switch. all this is doing is sending a signal to the microcontroller to tell it to turn on. So when the battery is installed, it is on all the time, constantly sucking a tiny bit of juice. So you want to be cognizant of that. If you're not using this tool, I would take the battery out so that you don't kill the battery. Now, here's the battery leads. We got the positive, the negative, and the T. Now the T terminal in the battery is the thermistor or the temperature monitoring. So that's going to be going into the microcontroller, and it will shut down if the battery gets too hot. Now you can see this has gone through a number of processes from the factory. Here's Celastic here. So this is a high temp, it won't melt, it actually has to burn. And that's just for mechanical strengthening, put it on the components to keep them rigidly in place. And then we have over here some hot snot, which of course just melts away as soon as it gets hot. But this is to, yeah, that's for that temperature probe there. Just the wire going to the board. So if this little guy isn't doing the switching, the main switching, what is it actually, what's doing the main switching? Well, it's one of these International Rectifier 1404s, this MOSFET in the D squared package. And here we have the TO 220 package, totally different package. This comes in reels, this comes in those slots, so totally different process. This could be put on by a machine, but this would have to be put on, this through hole would have to be put on by a human. Now, I've never seen this type of motor switching, a speed control circuit in a device, because it's kind of ugly. It's what those in the know would maybe call inelegant. So what we're doing is we're using this big heat-sinked MOSFET as a ka-chunk switch. And when you have a ka-chunk switch on a motor, you get this huge inductive voltage spike. You get a huge voltage spike. And the best way I can explain that is through an anecdote. Now, way before Christ was a cowboy, I was working at a place and we had electric forklifts, and they were battery-powered electric forklifts with actual ka-chunk contact switch. And of course, big fancy outfit, we had a contract for the maintenance. Somebody else did the maintenance on these things. So the maintenance company sent in a young fella, and one of the forklifts at one point was down, so he had a look at it, and he determined that one of the diodes on across the switch was faulty. So he, just to get it running, he took the diode out, and it still ran just perfectly fine. So he thought to himself, well, that's stupid. Why is there a diode in there at all? Now, of course, this wouldn't happen with an older fella, but with a younger fella, young, dumb, and full of cum, he put it on himself to go ahead and preventively take out these diodes before they blew up, because you didn't need them anyway, right? Well, lo and behold, 4, 6, 8 months later, all these contacts were welding themselves together or blowing up. What the hell is going on? We were spending a fortune on these contact switches. Well, of course, pain in the ass that I am, I get involved, start looking at the schematic, looking at the faulty switches, and of course the contacts on these contactors are completely burnt out, well, like just hideous. So I get looking at the schematic, and all of them, lo and behold, are supposed to have these big monster diodes across there to prevent this inductive kickback. Now I get looking on the machines, and there's no diodes on there. What the F, yo? So of course I get in there, X marks the spot, get on the old gargler, digi-key, get bigger diodes than required, jam them in there, bingo, bango, Jean-Guy's your uncle. There you go, hero for a day, and I'll show you exactly what's happening. Now the simplest way to think about this, say you got 100 amps worth of pixies dancing through here, what for turning the motor, of course this switch is closed. They're dancing through here, and then you open this switch, those pixies get angry, they got nowhere to go. This is a big inductor. An inductor, of course, stores energy in the form of magnetism. So when you open this switch up, Pixie's got nowhere to go. The voltage goes through the roof. Oh, it's very much akin to water hammer in your house. You got a whole bunch of water going, and then you turn the tap off all of a sudden. You get this big spike. And that's what this is, this big inductive voltage spike, sorry. Okay, so how do we prevent this inductive voltage spike? Well, there's a couple ways to do it, but the way we were doing it on the forklifts and the way the manufacturer did it was we put in a big beefy diode, like so. So the pixies couldn't get through this way when it was normally on, but then when you opened the switch, all that energy had somewhere to go. Whoop. And that prevented, it snubbed this inductive voltage spike. So if ever you're in an industrial setting and you see a burnt out diode and you take it out and the thing still works and you figure, well, that was fucking useless. It's not useless at all. It's preventing, this diode is protecting everything else in the circuit from getting this big blast of electricity. Now, it's always nice to have an inkling as to how something works. And you see this circuit board, and at first glance you go, whoa, I have no fucking idea. But it's actually a really simple circuit. It's nothing more than a switch. Just, that's it. All this crap is just the switch. And the switch is right here. It's this MOSFET. So what's going on here is we get power from the battery, and we power up this little microcontroller here, and the microcontroller is the brain. It decides when to turn this off and on. Now, the carrier frequency of the pulse width modulation is how many times per second this thing turns off and on, and then the duty cycle is how long it stays off versus how long it stays on for, and that determines the speed of the motor. Now, this microcontroller is taking an input from this potentiometer and then outputting however fast the thing wants to go. And there's no feedback. It doesn't know how fast this motor's turning. All it knows is the input from the battery to see how hot it is, this T terminal. It knows the voltage of the battery, so it knows when to shut off when the battery is dead. Then it also has this big shunt resistor here, and that's measuring how much current is going to the motor, so it knows to turn off if it's stalled or if it's something's wrong with it. And essentially, that's all it's doing. It's taking a bunch of inputs and deciding when to turn this guy on. Oh, and of course, the off-on switch, which it turns on this other MOSFET that actually gives power to the rest of the circuit. Clear as mud, right? Well, you don't really need to know exactly how it works if it fails, because chances are you can buy this whole board, or as I showed in a previous video, if you can trace the shit stain. If you see a shit stain, and chances are it's going to be either in this Schottky diode or this MOSFET or this MOSFET, and of course the numbers are highly visible, then all you need to do is solder those in and Bob's your auntie. They haven't, so it's nice they haven't cheaped out on the components themselves, but the build quality is actually pretty crappy. There's a whole bunch of different, like there's hot snot here, there's Celastic, there's some sort of conformal coating just sort of pasted on there. I see a wire here, it's got a loose dangly wire, just a piece of copper, you know, dangling in the breeze. That's no fucking good. So it's something, unfortunately, this was designed somewhere, and it was designed quite cleanly and nicely, and then whoever built it under contract didn't do a very good job. You know, good enough to get the job done, but really there's very little elegance in the assembly itself. And that just comes down to corporate culture, really. What are you willing to accept from a contractor who's building your parts for you? How much more does it cost to do this properly, neatly, and tidy? Very little additional cost, I would say, but that's the difference between a Milwaukee and a Fine, or a Milwaukee and a Hilti. Now this, because it's such a light duty tool, that's never going to affect the longevity. I wouldn't think, but it is there, and it is indicative of the type of process that they are willing to accept. So when you see the Team Spot reviews with the colors and the heavy rock music and this is the best in the business, super build quality, all that stuff, it's total bullshit. It's not super build quality. It's good enough. Just a boot to put the clamshell back together, and I noticed this is really cool. Look at these LEDs, man. They shoot up this way, so they're surface mount, but they're at 90 degrees. The actual part that shoots out the photons is pointing upwards, 90 degrees offset. That's very cool. I've never seen a surface mount LED like that. I finally got her, and the clamshell fits nice. We'll see if it works. I hope it does. You can see here, I noticed they actually made a mistake in the casting. in the mold that they didn't bother fixing. You see that? There's no reason for that cutout. No reason at all. So that's just another feature to wear out in the mold itself. It's surprising that they didn't catch that in the prototyping stage and fix it. But and I also see what for the clip is. It's because there's no fastener here and it's just all loosey-goosey, so you actually need this clip in there. Otherwise the battery probably will fall out, or yeah, kind of chintzy. When will they ever learn? Needs to go to 11. Okay, we're going to check the veracity of the claims on the label. What we've got here is a little piece of 3M tape and the digital tachometer. And then interestingly, it is infinitely variable. Once you hit 2, it doesn't go anywhere, but once you hit 2, it starts to go up. And again, all that's doing is increasing the duty cycle to get more voltage. More voltage equals more speed. I did see that woodworking fella there, the dorky fella, Matthias Wandel. He did a shill vid for Cambodian Tire, and there was a brushless tool on there, and the thing, it had 11 speeds. It went to 11, which I thought was pretty funny, but there's no reason why that wouldn't be infinitely variable. Like, why are there defined steps? It doesn't make sense to me. The only reason is maybe they're lazy on the control side, in that the potentiometer, you know, when it could hunt a little bit. So rather than take care of that on the control side, they just said, okay, well, we'll just have 11 speeds. A funny way to do it. There's 2. There's 15,000. It's all over the place. Yeah, pretty much faster than this thing can chooch. 16, 18, 21. Oh-ho! Oh yeah, 30,000. Okay. Right on the money. For once, they ain't lying. And I can envision in certain situations this would be incredibly useful on account of the battery power. And it's got no lack of power, even though it's on batteries. When I was a younger lad, I had the AAA version of the Dremel, and even then it was just junk. I think that's probably what put me off the Dremels altogether. But hey, thanks for watching. Keep your dick in a vice.